which is to try to prove the kind of interesting part of Giroux's theorem, the fact that every contact structure comes from an open book, and also this kind of equivalence with the fact that if two open books support the same contact structure, they must be related by positive stabilization. So to do this, if you recall, yesterday I said we're going to need the theory of convex surfaces, and we just introduced a little bit about that theory. So Stefan gave us a nice talk yesterday kind of explaining a lot more about convex surfaces, but I don't want to assume everybody kind of saw that. So I do want to kind of finish a couple of the facts I'm going to need in the proof. So here I've just written what I had at the end of the lecture last time, so don't worry, you should have it in your notes if you're taking them, except I reverted back to V since I don't have another V on the board now. So, so these were kind of three properties that the dividing set for a convex surface had. And recall the dividing set, so remember sigma is convex if there's a vector field transverse to sigma whose flow preserves the contact structure, and the dividing set is simply the set of curves along the surface where this vector field is contained in the contact planes. And there's some nice properties of this set, so I won't go through them again, but we talked about them last time. But you're going to see why I wanted that on the board now is because the next fact, which you didn't have on the board yesterday, is going to rely on those three things. So a singular foliation, so well, let F, let's see, so fix sigma convex as above, let script F be a singular foliation on sigma such that gamma sigma. So gamma sigma is the dividing set for the characteristic foliation, the dividing set coming from the fact that it's convex. So suppose gamma sigma divides script F. So what do I mean by gamma sigma divides script F? What I mean by that is that it satisfies those three properties except where you replace the characteristic foliation with script F. Okay? So let's see. So if this happens, then we can C0 isotope sigma such that sigma xi is script F. So basically any foliation that respects these dividing curves, you can actually take to be the characteristic foliation on the surface after some small isotopy. So this is kind of one of the most important facts about convex surfaces that makes them really powerful to use. And this, of course, as everything about convex surfaces that's really useful like this is due to Giroux. I probably shouldn't say that. I guess a few other people have done some useful things too. But so I mean a foliation is divided by a set of curves if basically these two things satisfy all three properties up there where the characteristic foliation is replaced by script F. Okay? Well, so the only so for instance, part 1 has nothing to do with the foliation, right? Part 2, what I want is the fact that gamma needs to be transverse to the foliation. And part 3 says there's some vector field that directs the foliation, so it's tangent to the foliation and it vanishes where there's singularities in the foliation. And there's a volume form on the surface such that those properties are satisfied. So that's what I mean by script F is divided by gamma. Okay? So we stated them for the characteristic foliation, but of course they make sense for any foliation on the surface, any singular foliation. And if a foliation satisfies those three properties with respect to some curve gamma, or multi-curve gamma, we say it divides the foliation. Okay? Other questions? All right. Okay, let's see. A few other facts we're going to need. So if gamma is an arc or closed curve on sigma, and all components of sigma minus gamma contain a component of the dividing set, then we may isotope sigma such that, or so that gamma is Legendrian. Okay? So we may isotope the surface so that we can kind of realize any arc or any simple closed curve as long as it satisfies this kind of non-isolating condition. You don't want it to have a component, a complementary component here that doesn't contain any of the dividing set. So this result actually happens to be due to Honda, and is quite useful in practice. We'll use it several times. Let's see. Oh, by the way, this has a name, and I'll probably use its name very often. This is called the Legendrian realization principle. And it's often abbreviated LERP, L-E-R-P. And LERP has now taken on kind of the properties of being a verb. So if you have a curve on a surface, you can LERP it, which means you isotope the surface to make it Legendrian. Okay? So I'll frequently talk about LERPing something to make it Legendrian. Okay. Yes. Okay, let's see. So if gamma is a Legendrian simple closed curve, or closed curve, well, simple closed curve, on sigma, then the twisting of gamma, so remember this means the twisting of the contact planes measured with respect to the framing given by the surface that the curve sits on, so this equals minus 1/2 gamma intersect the dividing set. So it's very easy to compute kind of the twisting by just looking at how things intersect the dividing set. So we have two convex surfaces. Their boundaries are Legendrian and their boundaries agree. Then we have the following picture. So here's one of the surfaces. Here's the other surfaces, and they're coming together at the boundary. I'm kind of thinking of them as intersecting transversely in this picture. So this is sigma 1. This is sigma 2. And if the dividing set is coming in here like this, then the dividing set on the other one is like this. So let me not write that in words, but basically what happens is along the boundary, the dividing set for one of them interlaces with the dividing set for the other one. So for any two endpoints here, there's an endpoint of a dividing set here and similarly here. So the top, in this picture, you should think of the top and the bottom of these, the picture as being identified. And if we smooth the corner, if we round the corner, then the picture becomes, so around the corner, so the surfaces are kind of glued together. And I guess to be really precise, I should kind of put orientations on this picture. So if these surfaces are oriented like that, then you have these four things coming in here, the four things coming in here, and somehow these things need to connect up, and they're actually going to connect up like this. Remember the top is identified with the bottom. So when you round the corners, kind of these curves migrate down and kind of connect up with those curves. So you'll wind up getting a convex surface, and you can figure out what the dividing curves look like after you round the corners. Okay. And let's see, we need one more fact before we can start trying to prove the theorem we're interested in. And this fact also is due to Giroux. So sigma, a convex surface, a small neighborhood of sigma is tight if and only if 1, sigma equals S2, and the dividing set is connected, and 2, sigma is not equal to S2, and gamma sigma contains no contractible simple closed curves. Okay, so no simple closed curves bound to disk. So this is a very nice criterion. One of them is quite easy to prove. It's very easy to prove that if either one of these things is false, then the contact structure is over-twisted, and it's kind of a fun exercise to try to do using the Legendre realization principle. It's not too terribly hard. There's one kind of tricky bit to work out there, but it's not too hard to do. The other implication is actually much harder. Okay, so we're finally ready to try to prove the following theorem. Giroux, 2000. So every oriented contact structure on M is supported by an open book. Okay, so every oriented contact structure is supported by an open book. So proof. To start the proof, we need a definition. So a contact cell decomposition of M, so a contact cell decomposition of M is a CW decomposition. Actually, well, let's just say CW decomposition of M such that the one skeleton of M is Legendrian. So of course it's some Legendrian graph. I mean, it's not a simple closed curve or anything. It's some Legendrian graph to each two-cell D has, well, first of all, notice the two-cell, its boundary is, of course, on the one skeleton, which means its boundary is Legendrian, so it has some twisting, right? And we want to have that twisting equal to -1. And lastly, we want C is tight when restricted to the three cells. What? What if the boundary of a two-cell gets collapsed to a point? How about the boundary of the two-cell is never collapsed to a point? And you can certainly arrange a CW composition like that. So yeah, arrange that it's not. Okay. So the first thing to notice is the fact that it's very easy to find a contact CW or a contact cell decomposition. So note all MC have such a decomposition. So why is that? Well, just cover M by a finite number of Darboux balls. So recall, a Darboux ball was simply a ball that was kind of contactomorphic to a ball, say, sitting in another contact manifold, in particular, sitting inside of the standard contact structure on S2, which we know is tight. So the contact structure on the Darboux balls is tight. So these are all tight. Of course, what I mean by that is the contact structure on them is tight when restricted to them. So take a CW decomposition with the 3 cells in the Darboux balls, in the interior of the Darboux balls. So you just, if you take any old CW decomposition, you divide it fine enough, you'll get it inside of this cover, the 3 cells inside of there, isotope, the 1 skeleton to be tight, or to be Legendrian, sorry. Okay. So far we've constructed a CW decomposition that satisfies 1 and 3. So the only thing you have to worry about is 2. So how do we arrange 2? Well, make each 2-cell convex, which we can do. Remember, if it was closed, you can isotope any surface to be convex. If it's got Legendrian boundary, you need to make sure the twisting is not positive, but I'll leave it to you to think about. In the situation I've arranged, the twisting couldn't be positive. That would actually violate the fact that it's tight. So if the twisting of a cell, of the boundary of the cell is not 1, well, if it's not 1, it actually has to be, or -1, it has to be less than -1, then subdivide. And what do I mean by subdivide? Well, so here's a 2-cell. So it's convex, so it has dividing curves, right? It has dividing curves, its boundary is Legendrian. How do I compute the twisting? Well, I think it's even still on the board. I can compute it by looking at this. So if the twisting is not -1, then there must be more than 1 dividing curve. So you have to have something like this or more arcs. And also you can't have any simple closed curves because that would violate tightness, and these are sitting on the boundary of 3 cells, so they have to be tight. So you have to have something like this. This is if the twisting is -2. And what am I going to do? I just draw this arc here. I Legendre and realize that arc, and I throw it into the 1 skeleton, and I use those 2 cells instead of, I use those 2 cells instead of 1 2-cell, and I've arranged the property I want. Because notice, of course, as I go around here, it intersects the dividing set once, so the twisting, well, actually in 2 points, so the twisting is -1 now. Okay? So it's very easy to arrange that you have a contact CW decomposition. Okay. Well, so let gamma, I probably shouldn't say gamma. Boy, but changing notes in the middle is not, or changing notation is not good, but okay, G, let G be the 1 skeleton of the cell decomposition. Okay. The ribbon of G, which I'll denote RG, and I'll drop the G probably in just a couple of minutes, but of course it depends on the graph, the Legendrian graph, is a surface such that 1R retracts onto G. 2, the tangent plane to R is equal to the contact planes at points P in G. So along the graph, R is tangent to the contact planes. And finally 3, away from it, they don't agree. Okay. So what does this look like? Maybe let me give you a quick little example. So we've heard in several talks how to kind of draw Legendrian knots in R3 by looking at their projection. So here's a Legendrian unknot in R3. And if we draw its graph, draw the graph associated to this, so this is a very simple situation, but we draw the graph associated to this, what does it look like? Well, if you remember, the contact planes are going to twist one time in a negative fashion as you go along here. And so if this plane is supposed to be, if this ribbon is supposed to be tangent along the... it should be R of G. What? P should be R of G. P should be R of... Yes, thank you. Thank you, sorry. So if R is going to be tangent to the contact planes as you go along, R is going to have to twist around -1 times as I go around here. And of course, since it's just a little thickening up of a circle, it's just going to be an annulus. So of course we have this. So if this is G, this is R of G. By the way, if anybody notices, that happens to be the positive Hopf band the way I defined it. So the boundary of this happens to be H plus equals boundary of R in this example. And remember, H plus is something that supported the standard type structure on R3. And that's not a coincidence. To finish the proof of this, all we have to do is prove the following claim. B equal boundary of R of G, I guess, is the binding of an open book for M supporting C. Okay? So that's what we need to prove. And if you happen to be goodbye, you probably are already done, and we can go on and move on to something else, because actually the fact that this happens to be a fibered, that the complement of this is fibered actually follows from a criterion of goodbyes. If you have kind of a ciphered surface for some knot or link, it turns out there's this property called decomposability that the Gabay came up with that guarantees that the thing is fibered, and kind of basically these facts of a contact cell decomposition guarantee that this is decomposable. But of course I don't assume that you happen to be Gabay, so let's actually kind of go through a little bit to try to justify the fact that the complement's fibered, and also the fact, I mean, you need to work a little bit, you need to also make sure that these contact planes can be isotoped very close to the pages of the open book, right? So let's try to see that. So let NR be, I'll write it in two pieces. That would be a small neighborhood of R. And I'm writing it in two pieces, so I'm writing it as a small neighborhood of B, its boundary, union the rest of it. So kind of the picture I want to have in mind here, let's see how well I can draw it here. So I hope this picture makes, well, let me maybe use a different color. So I have this kind of yellow strip here, which is a little piece. So this yellow strip here is a little piece of R. And then if I take its neighborhood, I'll have kind of a rectangular region, but I'm writing it kind of as a little neighborhood of the boundary regions. And then I'm kind of putting a little slab in between them. So is the picture hopefully relatively clear? Okay. So if what is N? So okay, this is the boundary region here. Maybe I should even use another color. So kind of the neighborhood of the boundary is just going to be in this picture two things. And of course I continue out and maybe connect up, maybe don't. So this is kind of this region here is NB, NB. And then there's just kind of a little slab stuck in between them to kind of give the rest of the region. So N is kind of this little bit in between. Okay? Is the picture clear? Okay. So let's see, where are we now? So if NB is sufficiently small, there's a standard model for C restricted to NB. So we're actually going to kind of ignore this piece. It turns out that the binding is kind of, or this B is transverse to the contact structure, and transverse knots kind of have standard models. I don't want to kind of go into that, but it's fairly easy to do. And basically this area is really well understood. The stuff we're really interested in is the complement of B, or the complement of the little neighborhood of B. That's what we want to see as fibered, and we really want to kind of understand the contact structure there. That's kind of the hard part. So we're going to concentrate on that. So now N, this region N, we can think of it as being R cross 0, 1/2, right? It's a small little neighborhood of a surface, so it's just the surface kind of fattened up a little bit. And if N small, if it's a small neighborhood, then R cross T and R cross S, if you look at the characteristic foliation on two different levels, they'll be the same. Because it turns out the foliation, what is the characteristic foliation on? So here's a little strip again. This is a little strip of R. The characteristic foliation, remember the core of it, the center of it's Legendrian, and tangent to the contact planes there. And then as you move out, it turns out you can actually arrange, if you'd like, that maybe everything goes out like this. And it turns out a foliation that looks like that is very stable. So if you move it a little bit, if you kind of move to a nearby surface, the foliation is going to have to look very similar to that. In fact, you can arrange it looks exactly the same. Okay? And by construction, C can be isotoped close to the pages. Well, I guess you probably can't read that when I move it up. So can be isotoped close to R cross T for all T. So why is this? Well, remember, if you just think about the original strip, the original ribbon, the tangent plane to the ribbon and the contact planes actually agree, right? And I just twist it, and the contact planes twist a little bit as I go out from the core, but they can't twist that fast, so as long as I make that ribbon really, really narrow, the contact planes are very, very close to the R already. And it's not too hard to convince yourself that because they're so close already, it's not too hard to make them arbitrarily close if you'd like. Of course, they can't agree with the tangent planes, but that's okay. But you can make them arbitrarily close. So somehow we see on this region N, it already looks like kind of a bit of a fibration. It's a fibration over the interval, though. So N is kind of fibered over the interval, and the contact planes are kind of supported by the pages of this little fibration over the interval, right? So what we've got left to do, we need to see that M, maybe M, what did I call it in the notes, just so you see that MR equal to M minus NR. So if you just remove this neighborhood, we need to see that this is R cross 1/2, 1, and C can be isotoped close to R cross T here as well. Right? So this will do it, right? Because in the small little standard neighborhood, everything's good. So we just need to see that outside that neighborhood, everything's good too. And of course, then the fibration of the complement of B is simply kind of R cross 0, 1/2, union R cross 1, 1/2, 1. And of course, 1 is going to be identified with 0 in the end. Well, so first what we need to do is so note, what does the boundary of NR look like? Well, so the boundary of NR is something like this, kind of locally. Right, so it looks something like that. And we know what the foliation kind of looks like at the top. At the top, the characteristic foliation kind of looks like this. And it looks like the same thing below, right? Well, it turns out this is a convex surface, kind of automatically, the way we've set it up. And the dividing curves happen to run right along here. So the red are the dividing curves for the boundary of NR. Okay. Okay. Well, so note, most of each two-cell, what should I call it? Well, lie or R is NMR. Okay. So most of the two-cell D is kind of outside this little neighborhood, right? So I mean, it's a very small neighborhood. So we will think of D as being on, we'll think of the boundary of D as being on the boundary of the neighborhood. Right, so D actually kind of goes inside this neighborhood a little bit, but it kind of goes in a very canonical way because this is a small neighborhood of the original graph gamma. So we can think of its boundary as sitting on the boundary of this neighborhood. And by LERP, boundary of D is still Legendrian. So boundary of D sitting on the boundary of this thing might not be Legendrian, but after we kind of jiggle the surface ever so slightly, we can make sure it's still Legendrian. So by hypothesis, the boundary of D has twisting equal to -1. So originally it had twisting -1, and again, so I only kind of retracted the boundary a little bit. It's still going to have twisting -1. So it intersects the dividing curves 2 times, right? Because remember, you can compute the twisting by -1/2 the number of times it intersects the dividing set. So here's a little piece of the boundary of MR, and I've kind of turned everything around now, so kind of MR is kind of inside of here, okay? So MR is some complicated thing inside of there. And on the boundary, we have some dividing curves. And this is the boundary of one of the disks D, and it intersects the dividing set in 2 points because the twisting is -1. And that means if we look at D, kind of abstractly, D is just sitting outside of here, and its dividing set has to look like this as well. And if you remember, what we said is when you have 2 surfaces kind of coming together, the dividing set is actually going to kind of be like that inside. All right? Let's now cut along D and round corners. So I'm cutting MR kind of along D, and then I round the corners and to kind of cap this off. And now the dividing set, it kind of came in here, and if you remember the way it kind of, they close up, it'll close up something like this. Right, when you round the corners, the ends of the dividing set kind of come together. So we get a new, so keep doing this. So if I keep doing this, what am I going to get? So if I have a 3-manifold, I remove its one skeleton, I cut along all the 2 cells, what do I have? The 3 cells. I have a bunch of balls. So keep doing this to get disjoint union of balls. So you have some number of balls here, just depends on the number of 3 cells we had. And what does the dividing set on these balls look like? So we got the dividing set by doing all this kind of cutting and rounding, right? So it could be anything a priori. But remember, we set these things up so that the balls had tight contact structures on them, right? Since they have tight contact structures, near the sphere, the contact structure is tight. And if you have a tight contact structure on a convex sphere, the dividing set has to be exactly this. There's nothing else it can be. So no matter how complicated this procedure was, and how many times we cut and rounded, you could imagine like thousands of curves here, but there's only one on each. Also, there's a nice theorem, or fact, I'll call it. So due to Eliashberg, it says there exists a unique tight contact structure on B3 inducing the characteristic, specific characteristic foliation. So if you fix the characteristic foliation on the boundary, there's kind of, that could possibly be the characteristic foliation of a tight structure. There's a unique contact structure that kind of fills it in. Okay, so there's a unique contact structure on all of these guys. Okay. That unique contact structure, there's a standard model for just sitting inside of R3. So there is a standard model sitting inside R3. And let me use R3 with kind of polar coordinates in the contact structure given by the kernel of dz plus r squared d theta. And let me take as the standard model that. So just take the unit disk, say, in the xy plane or the r theta plane, and cross it with, say, -1, 1. Okay? So kind of drawing this without the coordinate axes there. What do you have? Well, on the top, you have the characteristic foliation. You've got a singularity at the center, and then these radial lines running out. Same thing on the bottom. And on the boundary, you'll have some sort of slope here. But this thing is actually convex with dividing set like this. And notice what I can do. Remember, what is the contact structure like? Along the z-axis, it's horizontal, and as I move out, it twists a little bit. But it turns out, for instance, if you put a k in front of the r squared d theta and started making k incredibly large, what you'd wind up, you still have contact structures, but the twisting would happen slower and slower. So basically, these contact planes can be made arbitrarily close to these disk cross points inside of here. So basically, we've got some surface cross interval, and our contact structure can be isotoped arbitrarily close to the surfaces, to the disk. Okay? So basically, everything's great here. The only question is, can we go backwards? Can we glue these things back up and get the same property back on the original MR? Okay? So now glue the standard balls back together and see at each step we preserve the product structure and the contact condition, the contact property. By the contact property, I mean the fact that you can isotope it close to the surface. Okay? And I'm not going to go through that in detail. It's something that's best you should just kind of think about, sit down and think about it a little bit, but let me just kind of draw what's going on here. So you have these two things you're trying to glue together. You've got the dividing set here, the dividing set here. What happens is all the regions you're trying to glue back together are kind of little strips on the boundary like this. You need to convince yourself of that, but it's true. It's not too hard to work that out. And so, of course, when you glue things together like this, you preserve the product structure. And then you need to convince yourself that you can still isotope the contact planes close, but that's also not very hard to convince yourself of. Okay? So let me just kind of, at this point, exercise. Think about this. I mean, at this point, I really do think if you just kind of look at these pictures and think about them a little bit, you'll very easily be able to convince yourself that you can work your way back and actually get a product structure on M cross R that you can isotope the contact planes arbitrarily close to. Okay? So if you ignore the contact planes here, this process was kind of this disk decomposition that Gabay kind of had talked about.
Can you tell us where the pages are, or how they look like? The pages of the book?
The pages of this are just the disk. And as you glue back, here you just kind of identify, disk with disk, so you still have a disk page. But now if you kind of identified, if you had two strips in the same thing and you kind of identified them, you'd kind of add on like a one handle. And so kind of as you work your way back, you kind of construct the page. But the page, remember, in the end is going to have to be whatever this R is, because that R was one of the pages kind of on the other part. So we know what the page, one page is already. The kind of how it all fits together. It's not so easy to see, but okay. All right, so there's certainly a little bit more to think about to really convince yourself that this works, but I think this gives the basic idea of how to see what's going on here. Okay, well, let's look at some examples again. That's the end of the theorem, yeah. So we kind of finished off the theorem here. When you do that exercise, it's the end of the theorem. So now let's look at some examples. So remember, we looked at this example as notice this is a CW, a contact cell decomposition of S3, right? Because the one skeleton is this curve here. The disk, I'll put a disk in there, and then the complement is a 3-ball, so that's the cell decomposition. And of course, that disk, as it goes around the boundary, it has twisting -1, so it is a contact cell decomposition, which means if I thicken this up, this should be a page in an open book decomposition of S3 that supports a standard contact structure, and sure enough, as we noticed before, this is H+. Let's just look at one that's a little bit more complicated. So, on Josh's shark. So what do we do here? This is not a contact cell decomposition of S3, so I put a disk in here, of course. It has twisting -2. That's not good. So remember, what do we do if you have a disk that has too much twisting? You just kind of subdivide it. So there's a Legendrian graph now, and of course, the two disks are the disks that runs around here and the disk that runs around here, and both of those have twisting -1. So this is a contact cell decomposition. And if I look at its ribbon, I'll have something like the following. So this is a page in an open book decomposition that supports a standard tight contact structure on S3. And what is it? It's basically if you take two positive Hopf bands and you do the Murasugi sum of them, you'll get that. And as we know, that should be an open book decomposition supporting the standard structure on S3, and it is from this construction. Okay? And we could go on, but maybe I won't do more examples. But by seeing these two examples, we have the following really nice simple corollary. So L, a Legendrian knot in MC. So you have any contact structure, any contact manifold, you have any Legendre knot in that contact manifold, there exists an open book for M such that L sits on a page of the open book. Okay. And of course the proof of this is immediate. It's simply just make sure L is in the one skeleton of the decomposition of the cell complex. Right, and you can always do that. You take any CW decomposition, you add that to it, and add an arc kind of running to the rest of the one skeleton, and then just kind of subdivide enough to actually get another decomposition of the manifold again, and that'll work. And this is kind of an example in S3 of how you can do this. And of course now you can have a lot of fun. You can take, say, the Legendrian figure 8 knot or trefoil knot or whatever you want, and you can add enough little arcs so that you actually make sure you have these discs in there, and then you just fatten it up, and there's a nice CW decomposition of, or a nice open book for S3 on which the thing naturally sits, the knot naturally sits. So corollary, another corollary, any contact structure is supported by an open book with connected boundary. Okay, so why is this? Well, recall, if you do the Murasugi sum of two open books, you do the connected sum of the contact manifolds. So if I have an open book that supports a contact structure, which I know I have, and suppose it doesn't have connected boundary, well, I just Murasugi sum on positive Hopf bands, which means connected summing with the standard type contact structure on S3, which doesn't change anything, to connect up the boundary components. And you should convince yourself that you can do that, but it's actually quite easy. And that gives another corollary. This corollary is kind of a contact version of Bing's theorem, so contact Bing. So MC, Xi tight, is the standard contact structure, is the standard tight oh, sorry, we don't even need to assume that this is tight to begin with. So is the standard tight contact structure on S3 if and only if every simple closed curve is in a Darboux ball. Okay? So remember, Bing's theorem said a manifold, any manifold happens to be the 3-sphere if and only if every simple closed curve is contained in an ordinary 3-ball. Now I'm saying a contact manifold is a standard contact structure on S3. So first of all, I'm saying the 3-manifold is S3 and the contact structure happens to be the standard tight one if and only if every simple closed curve can be contained in a Darboux ball. And I should probably give a hint on that because there's one step that's maybe not so obvious. Hint, B pi supports MC, then C restricted to M minus a neighborhood of B is tight. So for the hint, you can take this as a fact and try to prove this, or you can also try to prove the hint if you like. It's actually not incredibly difficult to prove, but it does take a little bit of work. So. Sorry, yes, I do. Thank you, thank you. So contact structure is supported by an open book with connected binding. Yeah, thank you. Okay, so we're almost done with Giroux's theorem, right? We now know that there's a map from open books to contact structures well, open books mod positive stabilization to contact structures mod isotopy. We know it's onto. The only thing we have to show now is that it's 1-to-1. So that's the content of the next theorem. Well, actually, we need a lemma first. And of course, as always, also due to Giroux, given any open book for MC, it comes from the construction above after possibly stabilizing. After possibly positively stabilizing. Okay? So just due to the fact that we don't have a lot of time left today, let me not bother to prove this. It's not actually terribly hard, and just the quick hint is start by taking kind of the page of the open book is some surface with boundary, right? And a surface with boundary certainly retracts onto a graph. So take that graph on one of the pages, Legendre and realize that graph. You can actually do that. And then try to prove that that's the one skeleton for an open book for a contact CW decomposition. So that's what you should try to do. And let me not do that, but I will leave it to you to think about. But let me move on. Once we have this lemma, it's actually fairly easy to prove. Yes, so you take a page. The page retracts onto a graph, right? Because it's a surface with boundary. So take this graph on one of the pages and Legendre realize it. So this is now some Legendrian skeleton, some Legendrian graph. My claim is this is the one skeleton of a CW decomposition. So first of all, you have to prove that that you can get a CW decomposition that's the one skeleton of. Then you should try to prove that it's a contact cell decomposition. And if you run into trouble, you might have to stabilize. But I actually don't think you have to stabilize. I only put that there because I think in previous statements people have said that. But I don't think you need the parenthetical comment. But I'm just putting it there to, again, cover bases. But okay. So what I'm saying is I don't think you do, but I haven't very carefully gone through the proof that you don't. So let me put it up there because, again, I think other people put it there, but I think they might have put it there because, well, again, just to be cautious. But I don't think you need the parenthetical comment there. Okay. So let's just kind of try to finish up. Let's see. So theorem, and again, Giroux, 2000, 2 open books supporting MC are related by positive stabilization. And the proof can assume both come from a contact cell decomposition and any two contact cell decompositions are related by the following. Oops. So the first thing you might have to do is subdivide a cell, a 2-cell. So you have a 2-cell here. We can think of it, since it's a contact cell decomposition, as a convex surface. So I'll put the dividing curve on it. You can divide it, and the way you divide it is as follows. So you add this add that one cell into the decomposition. 2, add a one cell C and a 2 cell D to the decomposition such that boundary of D equals C union C prime, where C prime was an arc in the one cell, or in the one skeleton of the cell complex. So the idea is you've got this part of the one skeleton, and you just kind of add on an arc and a disk like this. So there's C, here's C prime, and that's D. Okay? And lastly, three, add a 2 cell with boundary on one skeleton. Okay, so that's what you do. And exercise. Show 3 does not change the open book. So what I mean by that is, of course, given a contact cell decomposition, you actually get an open book associated to it. And if you do move 3, you don't change the open book associated to the cell complex. And part 2, show 1 and 2 give a positive stabilization to open book. Okay. So let me not go through that because I'm essentially out of time. But once you know that cell decomposition can be related by these 3 moves, it's fairly easy just to kind of check locally. Because you can see this is all a very local thing because everything happens in kind of the neighborhood of a disk. And you just need to make sure that what's going on there is just a positive stabilization. And it's not too hard to do that if you go back and think about the construction. So that actually finishes Giroux's correspondence. And I guess that's where we should end today. Any questions? Yeah?
Does this mean that if the time over-twisted disk?
It has to intersect the binding, yes. Yes.
Are there any theorems relating to, say, the framed isotopy, or the regular isotopy class of the Legendre and not in the corollary you had of that, and the ambient isotopy of the class of B that comes from the binding? Nothing that you can say, given an L, B will look something like that?
No, I mean, you might have to, I mean, even in S3, if you're given a complicated L, the open book you construct could be really crazy. So yeah, I would be surprised if you...
Exactly how, say, a positive stabilization affects the binding?
Yes, positive stabilization. So that's actually pretty easy to work. And the example we did actually generalizes. Kind of when you add that little kink in there, it'll make you stabilize the binding, or stabilize the book by H+. All right.